Hi-oh, here we are talking about vectors. And if you pause the video and read the Foxtrot cartoon, you'll find that even Bill Amends understands a little bit about vectors. First off, what's the difference between a vector and a scalar quantity? This should be nothing new. We've talked about this in the past. Scalar quantity just tells you an amount, and of course an example might be gallons or a length, things like that. And these things they just tell you how much. It doesn't make sense to say what direction, for example, what direction is your length. That doesn't make sense. So that's a scalar quantity. Compare that to a vector quantity, which tells you not just how much, but if you can ask the question, what direction is the blank, then it's a vector quantity. So it not only tells you the amount, but it tells you that direction. Example, what direction is your velocity, your force, your acceleration, those type things. So let's go ahead and add these things together. Let's see what we have. Well, when you add things, at least vectors, you want to place them head to tail. Now think about this, what this means. That if you have an arrow, don't want to show him yet. If you have an arrow, and let's put him up here, an arrow, the tail of the arrow is this way, and the head of the arrow is the other way. Well, we're going to treat these arrows or vectors like dogs. Because a dog has a head, a dog has a tail, a dog can point a direction, right? We have a pointer, and so his head points to the direction. His tail doesn't do that. So what do you do when you see, or what do you see when two dogs get together? They, of course, follow the rules of vectors. They go head to tail. And it doesn't matter if they're parallel to each other or perpendicular, one will inevitably try and still go head to tail. The result of that would be through here. In other words, if you now imagine a dog walking to the left and then walking up on our picture, the result would be up and to the left, and that's our resultant right here. Cartoon Savage Chickens shows this pretty well. Even the machines from Star Wars know how to add vectorially. So, as we mentioned to review, your result is such that the exposed tail goes to the exposed head. That's the resultant. Exposed tail goes to the exposed head. That's the resultant. With the top one, right? Exposed tail goes to the exposed head. The resultant is these two together, which would be 120 to the left. And exposed tail to the exposed head, here is your resultant right here, which should be 80. Had to throw this in. Moe, Larry, and Curly. We know force is a vector. Therefore, what is the net force? We know that Moe pulls. So here's Moe. He's pulling with a force of 100 newtons. And Larry is pulling with a force of 20 newtons. Just like in our previous, you can put them so they're head to tail. And the result is exposed tail to exposed head for a total of 80 to the left. Let's do it this time with a flying hot dog. Flying hot dog attempts to fly north, so you want to draw it as you hear it. Flying north, north is up, 8 kilometers per hour. But at the same time is pushed east. So he goes north and he goes east at 6 kilometers per hour. what's the resulting velocity? What's the resultant? Well, you go from the exposed tail to the exposed head, from the tail to the head, and this is our resultant right here. And of course, you do the Pythagorean theorem. This side, we'll call it side C, is equal to the square root of 6 squared plus 8 squared. And of course, when you solve that out, you're going to get 10. So let's put this in terms of direction now. We know how to find the resultant, but what about the direction? We know our hot dog was pushed north at 8, and we know the wind pushed them east at 6. We know that there's a resulting velocity of 10. Notice the resultant is bigger than either one of those two. You're actually going to go faster because the wind is helping you out. So what is this resulting direction? This is north, this is east. Notice we end up east of our original northern direction. So we're trying to find that angle right there, the one with the exposed tail. Well, let's use our original values. And we have to talk about SOHCAHTOA. We know that the tangent of the angle we're solving for is equal to the opposite side over the adjacent side. And since we want to know the angle, we have to put that alone. The angle alone is the tangent to the -1 times the opposite side over the adjacent side. Plug in those values. Tangent -1. The opposite side, of course, is 6. The adjacent side is the one left over that isn't the hypotenuse, which is 8. And you find that equals about 36.9 degrees. So it's 36.9 degrees east of north. So let's do a review and talk about what happens if, well, you don't know, or it's not exactly perpendicular, we can't use the Pythagorean theorem, something like that. Well, we know the top one, of course, is, well, exposed tail to exposed head. There's our net resultant, and of course, that's 14. And the next one is, hopefully you figured it out to be 6. So those are our maximum values. We know that everything's moving to the right, it's 14. Half of it is moving to the right, the other half is moving to the left, that's 6. Those are minimum and maximum. And when we solve for the Pythagorean theorem, we get 10.77. Look at that 10.77 is halfway in between. So what do we know about this next one? Well, we know straight up is 10.77. We know straight out is 14. So in this class, it's acceptable to say that the answer is somewhere between 10.77 and 14. Likewise, we know here is 10.77. And we know when the arrow is completely this way, it is 6. So it's okay in this class to say it's somewhere between 6 and 10.77. Lastly, this is a pretty tough idea. Notice the boats take the same amount of time to get to the other side of the shore. Notice that the time it takes for the boat to go upriver as the current pulls it is the same amount of time it takes for it to get across the shore. Meaning the times are the same. The time is the same here, the time is the same here, the time is even the same there. It's a key idea. So if we're talking about velocities here, the time is the same, velocity is distance over time. Look at that, you have a greater velocity because the distance you need to go is greater. The time did not change. So as that increases, the distance, so does the velocity. Alrighty, that's it.